Welcome back, ladies and gentlemen, to the last episode of this mini-series that we are covering with Taylor and Maclaurin's, and after a long time waiting, 3 videos and counting, we are finally ready to unveil the Taylor series to you. The Taylor series is basically the Maclaurin series, and I'll even paste it in. The Taylor series is like a Maclaurin series. In fact, they're almost exactly the same. It's the polynomial estimation of a non-polynomial function, but this time it's no longer centered at x equals 0. So if we review from the last couple of videos, if we look at the Maclaurin shortcut, that was p of x is equal to f of 0 plus, and I know I called the next piece f prime of 0 times x, but in reality I'm going to call it something different to make it look more like the Taylor series that we're going to be dealing with. I'm going to call it x minus 0, which is basically x, and so again we're just doing it to make it look more in line with what we're going to do with the Taylor series. So f double prime of 0, and then x minus 0 squared over 2 factorial, plus f triple prime of 0, x minus 0 cubed over 3 factorial, and then I'll just go ahead and do another one just because I feel like it, x minus 0 to the 4th over 4 factorial, and so on and so forth. Well, notice how 0 is going into f and f prime and all those other places, and x is literally being shifted either to the left or to the right by 0. Well, the Taylor series does exactly the same thing, and in this case I'll call it capital T of x just to make things distinguished. And in fact, speaking of distinguished, I'll go and change colors just so that we can see it better. I'm going to call him f of a instead, and this time I'm going to center him around x equals a. So what happens is I end up getting plus f prime of a and then x minus a plus f double prime of a x minus a squared over 2 factorial, and it's the same thing. It's just like a Maclaurin series, except it's no longer centered at x equals 0. So we end up, whoops, not 4, a to the 4th over 4 factorial. And I just realized I forgot the of 0 part in that derivative there. My apologies. That's it. That's the Taylor series right there. We're just centering it somewhere else. So let's go and take a look at a couple of concrete examples, and then we will close it up. So my Taylor series here is going to be a representation of f of x is equal to sine x. And this time I'm not going to center him at x equals 0. I'm going to center him at x equals pi over 2. So from here, what I'm going to do is I'm going to derive this guy a couple times. So I'm going to say f prime of x is equal to cos x. F double prime of x is equal to negative sine x. F triple prime is going to be negative cos. And then the 4th derivative down is going to be regular old sine back. And so how does this look? Well, if I'm going to center him at x equals pi over 2, now I've got to do a little bit more thinking. It's not going to, especially because of the sines and stuff like that, and the cosines becoming 0 or 1 depending on where I'm at. I'll go ahead and say t of x, t for Taylor polynomial, f of pi over 2, plus f prime of pi over 2, and that's going to become x minus pi over 2, plus f double prime of pi over 2, and x minus pi over 2 squared over 2 factorial, plus f triple prime of pi over 2. And again, I'm really only doing as many as I need to get to a pattern here, and I'll probably just go to the first 4 or 5 non-zero terms, and then that way we can kind of see where this goes. It should be cubed over 3 factorial. So again, I'm just going to start to evaluate this now. So what do I get? That becomes t of x equaling, what's f of pi over 2? Well, instead of 0, like it normally is for sine, this is going to become 1. And then f prime of pi over 2, well, cosine of pi over 2 is nothing, so this guy's all the way gone. And then f double prime of pi over 2 is going to be negative sine of pi over 2, so it'll be negative 1. So negative 1, and it's going to be x minus pi over 2 squared over 2 factorial. And then the triple prime is going to be cosine, so that's going to be nothing. The quadruple prime is going to be back to sine x. So it's going to be positive 1, and we're going to have an x minus pi over 2 here. And since we skipped the 3, we'll go to 4 and over 4 factorial here. And I think we're going to kind of see a pattern emerge here. We end up getting x minus pi over 2 to the 6th over 6 factorial plus x minus pi over 2 to the 8th over 8 factorial. So let's talk about what this thing's actually doing. Well, remember, the Taylor series is basically a Maclaurin series that has a center not at 0. If I look at this thing, if I'm centering him at pi over 2, that's why all of these terms are being shifted to the right by pi over 2, because the minus pi over 2 on the insides of these x's, on the insides of all these x's here, the minus pi over 2, helps recenter this graph at pi over 2. Just like our horizontal shifts when we do any type of graphing. So from here, let's go ahead and see what this looks like in the Inspire. And here we are with our nifty TI Inspire right here. If you notice, I've kind of already shortcutted this thing by putting all the terms in. I put it in through 8, which is where we got it through. And I will go ahead and click the Go button to see what this thing looks like. So, hello. Very cool. So, from here, notice it looks like a polynomial because it is a polynomial. However, if we look at certain aspects of this thing, there are sine-esque aspects to this graph. If you look at here, the wave going down, then up, then down, it looks like we're getting a really, really close approximation of sine. And of course, the more terms I tack onto this function, the more sine-y this graph is going to look. So from here, I want to go ahead and zoom in on this graph here. And let's go ahead and change our window settings from 0 to 2 pi. And I'll go ahead and make my ymin negative 1 and my ymax 1. Now if you notice, I'm going to get rid of him because we don't need him. Now if you notice, he really looks like sine right here. Like he really, really does. But what I want you to also think about is what the function actually was. From here, notice how it started off at 1 and then became x minus pi over 2 over 2 factorial being squared. 1 x minus pi over 2 to the 4th over 4 factorial. Well, we've actually encountered a Taylor or Maclaurin series that behaves this way. We've seen it before. We've known it as cosine. If you remember correctly, cos is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus blah, 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 blah. So notice the correlation here. It looks really similar. In fact, this t of x, our sine function that we are approximating with the center being at pi over 2, looks a heck of a lot like cosine. But why is that? Well, it's because back in honors pre-calc, when we had you, I want you to think back to that class, when we had you writing equations of trig functions based on the graph, and your Calc AB teacher would ask you, well, what type of graph is this? And someone would raise their hand and say sine. And then someone would raise their hand and say, no, wait, but it could be cosine, depending on where you started. Notice how right here, if you started at 0, this thing would be sine. But you could start at the hump right here, the maximum of the graph, and let it effectively become cosine. Well, where I'm going with this is, if I was to modify my cosine of x, and this is getting a little bit ahead when we get into Taylor and Maclaurin manipulation, if I did cos of x minus pi over 2, could I effectively be 1 minus x minus pi over 2 squared over 2 factorial plus x minus pi over 2 to the 4th over 4 factorial minus x minus pi over 2 to the 6th over 6 factorial. Is it possible that this could be this, and all I have to do is replace an x with an x minus pi over 2, and then I end up getting a shifted Maclaurin series, in other words, a Taylor series? In other words, does this function here equal sine? Well, let's find out. We have some trig identities that might allow us to find out if that's true. Well, from here, I'll go ahead and change colors here. If I look at cos of x minus pi over 2, and I will get rid of him, this little line. Well, I could go back and talk about our good old buddy, the sum and difference formula, and expand him. And I could say cos of x cos of pi over 2, we're minus on the inside, so it's going to be plus, sine of x sine of pi over 2. Well, cos of pi over 2 is nothing, and sine of pi over 2 is 1, leaving me with sine x. So, what am I getting at here? If I center my sine function at x equals pi over 2, it's exactly like getting a cosine of x minus pi over 2. So sine, in other words, sine is cos of x minus pi over 2 based on a co-function identity. And the Taylor and Maclaurin series will behave the exact same way. So just another way that these things are all interconnected. So I hope you found that interesting. I'm going to do another example real quick, so let me just clean up the board. And welcome back. We are going to do this last example here. Our function here is f of x equals e to the negative x. We're going to write a Taylor series summation for this non-polynomial function centered at x equals ln of 2. And so we're going to do 3 things here. We're going to take care of the first 5 non-zero terms. We're going to list them out. And then I'm going to find the general term. The general term is basically the term that allows me to find any term in the sequence. So we did this back when we first started sequences. So we'll find that out, basically finding a formula for this sequence. And then we'll write this thing in summation notation after finding the general term. So let's see. Before I get started, I'm going to go ahead and take a few derivatives of this thing. Now, it's not going to be as simple because there's going to be a little bit of chain rule going on. But f prime of x will be negative e to the negative x because of our good old buddy chain rule. F double prime of x is going to be e to the negative x. And I think we're just going to see this alternation happen here, but I'm going to write out the first few anyway. And even though we have these shortcuts, I still think that there's value in writing some of the derivatives. That way we're sure of where we're at. So next I'm going to go ahead and write the Taylor version of this. So it's going to be t of x equaling. Now I want the first 5 non-zero terms. Now I'm pretty sure that nothing's going to produce a 0 here. So I will just go and write out the first 5 and then call it at that. So it's going to be f of ln of 2. That's term 1. Next is going to be plus f prime of ln of 2 times x minus ln of 2. That's term 2. Term 3 is f double prime of ln of 2. And then x minus ln of 2 squared over 2 factorial. And then plus f triple prime of ln of 2. And then x minus ln of 2 cubed over 3 factorial. That's 1, 2, 3, 4. That's okay. I think we're going to be able to figure out what the fourth term is. Okay, so from here, I'm going to go and write out the first few terms. F of ln of 2. Well, what is that? Well, that's e to the negative ln of 2. Contrary to popular belief, that is not negative 2. This guy's going to jump in. We get e to the ln of 1/2. That gets me 1/2 here. Now, the next one is going to be, for f prime, it's going to be the negative version of that 1/2. So negative 1/2, and then x minus ln of 2. And then plus f double prime is going to be the positive version again. So it'll be 1/2 x minus ln of 2 squared over 2 factorial minus 1/2 x minus ln of 2 cubed over 3 factorial. And then I got 1, 2, 3, 4 terms. My fifth term is going to be plus another 1/2, I would suspect, and then x minus ln of 2 to the 4th over 4 factorial. So off the cuff, I can tell you right now, something that is really distracting is all of these extra 1/2s that are everywhere. Like, these are really distracting. So since every term is suspected to have a 1/2, I will go and factor that 1/2 out. And what that gives me is it gives me 1 minus x minus ln of 2 plus x minus ln of 2 squared over 2 factorial minus x minus ln of 2 cubed over 3 factorial plus x minus ln of 2 to the 4th over 4 factorial. Now, why does that help? Well, it helps because now I'm able to kind of determine what this series is going to look like. And by the way, that should be a 2. I know it looks like a 3. It's a 2. Clean it up. Clean it. So let's go ahead and see how this thing is advancing. Well, I know that for my general term, I know that there's going to be an alternation happening because we're going plus minus plus minus. So for now, I'll go and just start it off with negative 1 to the k. And I know that there's a 1/2 involved every single time because if I distribute the 1/2, there's going to be a 1/2 involved. And the x minus ln of 2 always seems to be there. And it's going to be divided by something. Now from here, if I leave it as this, if I leave this as k, if k was 0, that would get me a positive value here. So I could start this thing at k equals 0 and let this become 1, and then 2, and then 3, and then 4. So I could effectively call him k factorial on bottom with a k value exponent. The first term is 1, the second term is 2, 3, 4. This would be fine as long as you said k begins at 0. Most people, though, don't really want to begin the k at 0. Most people are used to and comfortable with, for very good reason, with k being starting at 1. So if that was the case, then you could also do this and have it be just as effective. You could say k plus or minus 1 to ensure the positivity of the first term. And then you know the 1/2 is going to stay there the whole time. And again, it's just like sequences. We have to just kind of finagle this and try and make it make sense. If this is k equals 1, then the second term is going to be k equals 2, which means this would have to be k minus 1 here. And then instead of k factorial, it would have to be k minus 1 factorial here, with k beginning at 1. I would take either one. It's not a big deal. Most people are partial to this one because it's rare that we let k begin at 0, so I think some people are just more comfortable with letting k begin at 1. Either way you cut it, I'm okay with it. So then the last thing is, so this was part B here, the last thing is the summation notation. Well, we already have our term here, our general formula, so I'm going to go ahead and I can kick out the 1/2 like that, throw down the summation from k equals 1 to some n, and it would be negative 1 to the k plus or minus 1. It doesn't really matter. I'll do minus just to keep things consistent. So I'll just say x minus ln of 2 to the k minus 1 over k minus 1, k minus 1 factorial. So, to summarize, a Maclaurin and a Taylor series is just a polynomial representation of a non-polynomial function. Please remember that the Maclaurin series is centered at 0 for the polynomial, and that the Taylor series is not centered at 0 for the polynomial. And I believe that will wrap up this mini-series. So as always, guys, leave any comments or questions in the comments area. I would love to hear from you as always. And be sure to check out any of the past videos if none of this stuff makes sense, or if you have any things you need to iron out. And I will see you in the next episode. See you later.